started because we've got 40 minutes and we've got quite a few things to go through. And so we're here to talk about, so going back to the name of the panel itself, the compute collision. And so I wanted to address it through a few different angles, and we've got quite a different mix of speakers here with us today. So, for half a century, Moore's law, our ability to double transistor density every 2 years, was the free lunch that let software grow almost without restraint. And so, if we're here today at Raise, it's to talk about AI, and that's changed a bit of how we approach those topics today. AI, an unusual hungry guest. We've been talking a lot about how the frontier models cost tens of millions to train, the constraints that they have. And so if you guys are happy with this, what I'd love to suggest as a thread for our conversation today is to go through a few of the different collision threads that are interesting in the context of compute. And so the first one that I'd like to dive into would be to push the classical silicon further. But before we do this, maybe we could go through a quick round of intros, just so that the participants here can tell you guys, the audience, a bit more about why you're here and how you can contribute to the conversation. Maybe, Jean-Laurent, you'd like to start first.
Good morning. Thank you for inviting me. I'm Jean-Laurent Philippe. I'm the EMEA CTO for Intel, and I work mostly on the product side of Intel. But I can talk also about Intel Foundry, and we'll talk probably about that.
Good afternoon. My name is Will Abbey. I'm the Chief Commercial Officer for ARM. AI is fundamentally changing the world that we live in today. I'm passionate about understanding the limits of where we are and how we can advance that as an ecosystem.
Thank you for inviting me. My name is Elad. I'm the founder and CEO of NextSilicon. In NextSilicon, we develop a next-generation compute chip, one that drives supercomputing, HPC, AI and machine learning, and more. Really excited about that and the future.
Yeah, pleasure to be here. I'm Pete Shadbolt. I'm a co-founder of PsiQuantum. We're a Silicon Valley startup and building a giant quantum computer.
And on my end, I represent Lightspeed, a global venture fund where we invest across the stack. And so happy to be here. So let's get started. So, as we've discussed, Moore's law is slowing and AI compute needs are exploding. As we get closer to the point where classical chips seem to not being able to keep up, do we believe that chiplets, 3D stacking, new materials are approaches that could move this a bit further? If I bring it to you, Jean-Laurent, first, talking about CPUs and GPU roadmaps, could you maybe tell us a bit about how we can push this frontier further with the existing architectures?
Absolutely. So I'm happy that you asked this question because Moore's law comes from Gordon Moore in 1965. So 60 years ago, he predicted that the density of transistors would double every 2 years or something like that, plus or minus a few months. And since then, it has, nearly. But people have also equated that to it is capable of bringing more performance over and over each generation, and it is the case. So at Intel, we have done Intel 7, Intel 4, Intel 3, and we are getting into production with Intel 18A, which is 1.8 nanometer or 18 angstrom. And we are getting there. We've announced that we will put it in production at the end of the year with our first Intel Core Ultra CPU, which is capable of AI, which is called Panther Lake, and it's going in the right direction. We are already working on the next generation, Intel 14A, but at the same time, it's not only the number of transistors, it's what you do with them. So that's why in all of our processors, for now several generations, we have introduced or integrated some AI accelerators with AI instructions and everything that goes on top of it. So that's why we believe that Moore's law keeps on going and helping with the needs that are coming for the end users. Packaging is also another way of using Moore's law more efficiently by stacking or connecting different chiplets. We don't have time to talk about that, but I'll be happy to talk with anyone who has some questions. And we also have here on our booth some people who can talk a little bit more about Foundry than I.
And Will, on the topic at ARM, when I think about ARM, I often think about efficiency. And I'd be curious to hear if you believe that transistor scaling is plateauing, and if it is, how are you guys thinking about addressing that?
Yeah, so the industry saw signs that scaling was coming to a physical end. I agree with some of the comments my colleagues already talked about, but the reality is that when we got to around 28 nanometer planar, we already saw the signs that logic scaling was going to run out. We fundamentally saw it at 7 that it was beginning to break. And as you move to 2 nanometer and beyond, it is clear that memory is not scaling. Logic, in order to get it to scale, you need to go to different materials, gate-all-around technology. And so we look at the problem fundamentally differently. And so when you think about AI, you start to think about tensor operations, machine learning operations, and this idea of a general purpose workhorse like a system on a chip that we've known that's made mobile possible doesn't work anymore. So you need to think about it fundamentally different. At ARM, we've always had the view that power efficiency or performance efficiency is key. We had no choice in the early days because of the mobile form factor. And so when you think about the fact that power is a scarce commodity, when you think about performance is a key to run high-performance, complex workloads, you need to start to think about first principles. And so ARM is all about power efficiency, and power efficiency is making a difference. But then we go beyond that and start to think about custom silicon. And for us, it's compute subsystems. When you think about what the hyperscalers are doing, it's this idea of taking a general purpose architecture, but then augmenting that general purpose architecture with a custom approach to solving real world problems, which is what AI really needs.
And Elad, I'm realizing now as we're going through this, we're progressing gradually to the existing paradigm is challenging. But Elad, on your end, I think when we were preparing for this session, there was a bit of a conversation around how we need a fundamentally different paradigm, and you seem to hold this as a quite strong opinion. Could you speak a bit to those ideas and how you feel about it?
Yeah, absolutely. Well, what an incredible time we are in. Models are growing and growing, and we need more compute, and we need more compute to fuel science, innovation, progress. That's reality. And the way that we are trying to solve these matters is by trying to innovate in brute force hardware. Let's put more transistors. Let's take CPUs and scale them, and let's add tensor core to execute them and go to 2 nanometer and 1 nanometer and just go down in the frequency, but power is going up because more transistors means more power is going up. Frequency became harder, so we try to put more of them, and then we go to infrastructure problem as cooling and building 1.21 gigawatt power plants next to the AI factories. Well, I don't think that that's the solution. I think that the solution, and probably Pete, as the quantum expert, is going to say more, is fundamental new architecture in the innovation layer. We can add more CPU core von Neumann that schedule instruction. We can take those CPUs and have a smaller one, GPUs with different memory model and custom AI ASIC. But it's going to take you to a step. New architecture, like the one that we do, that is based on software, might fuel the future.
Makes for a good transition for you as well, right? I think there's different approaches around photonic and quantum-inspired architectures. Of course, you have that direction that you're pushing. Could you speak a bit about it?
Yeah, I mean, I think I'm lucky to work a little closely with semiconductor industry, new materials, exotic packaging, some of the things that have been discussed. And I think there's a lot of excitement around those opportunities, but they're limited. They're a crutch against something that is ultimately not going to continue indefinitely. And I think it's pretty striking, actually, that people are not more afraid about the end of Moore's law. Like, to me, it looks like, an impending catastrophe for something that has been assumed as an inevitability for decades. This is why myself and my colleagues and many people around the world have spent their lives trying to realize a quantum computer, which is that it gives us hope that we can actually break out beyond that final frontier. And it's easy to forget that, of course, we used to do computing with the abacus. We used to do mechanical computers. We used to do vacuum tubes. And so, yeah, we know that it is possible to build machines that fundamentally change the arithmetic of what you can do with computation. And I think it's pretty urgent that we do that, given everything that we just heard.
I think if we think about the opportunity broadly across the AI stack, there generally is a discussion between this kind of a brute force approach and then the smarter approach, and then it applies across energy, it applies across design. There's a bunch of different approaches there. Jean-Laurent, maybe you could talk a bit about how if we are hitting those diminishing returns, how are you able within Intel, but also just broadly how you're thinking about the opportunity, thinking about hardware, software design, and how the software layer can also overcome some of those challenges in a smarter way rather than just brute forcing your way and solving for those problems?
Yeah, absolutely. So indeed, we can add more cores, more transistors, and hope that we can get more performance. But if we look at the transistors, we know how to design them. As you said, gate all around, power vias. In our new manufacturing technologies, we are able to increase the performance by about 15% just by the new technologies that we are innovating with in our 18A manufacturing process. But what is important is that once you understand what the users want to do with your hardware, then you know how to design it, manufacture it at a cost at the end, which is interesting and accessible. And then we at Intel, we co-design hardware and software. Not the software at the highest level, but all of the layers that are needed for developing the applications or the solutions that we will use. So we co-design the firmware, the drivers, the tools, the compilers, the libraries. And typically, when you look at AI for inferencing, because we didn't talk about that yet, but I see two things very different. Training, which is requiring some pretty big power plants for the data centers, and then the inference. The inference that you do on your cell phone, on your laptop, the inference that you do as much as possible at the edge, locally. And that will save a lot of power if you can do a lot locally. So on the Xeon 6 server processors, you can do a lot of inference for LLMs or SLMs up to 20 billion parameters. On your Intel Core Ultra-based laptop with the NPU, the neural processing unit that will consume very, very few watts or milliwatts to do the inference, you can do it locally. Last week, I don't think that I have my colleague here, but I was at another event, and I arrived at 11:30 to do a talk at 2. I got a laptop delivered at 12, and I installed a RAG. So the AI builder from Intel, open software, the Hugging Face LLM, the information that I needed for the RAG, and within 45 minutes, I had my laptop working with RAG, and it could run my RAG locally without going to the cloud. So that's why we believe at Intel that inference at the edge, where the data is, will be very interesting. So the co-design software, hardware, and understanding what people want to do is key.
And maybe that's just going a bit off track, but because initially I was thinking about this as a separate conversation point, but it feels that as we're talking about inference and edge, there is this conversation of edge versus cloud in a way, and I'd like to broaden it up to any of you here. How do you feel about this edge conversation? And as we think about the compute needs, the electricity needs, edge seems to be like a potential solution in efficiency and smaller models.
Yeah, I mean, I'd like to perhaps give a perspective. So I talked about the importance of power efficiency. And so this idea that models are going to just continually get smaller and smaller and smaller is true. But I also think that as we start to think about new use cases and breaking new grounds, models are also going to get bigger. So it isn't going to be this idea that everything gets smaller. models are going to become more complex, different architectures in the cloud, as well as endpoints. And so you have to constantly think about power efficiency. It is a scarce resource, and so designing from a first principle perspective around energy and power efficiency is key. When you start then to think about endpoints, and again, I agree with a lot of the comments that my colleague has made, but the fact that 300 billion devices right, at the edge are based on ARM, and the fact that we think about power efficiency at the edge, I think gives us an inherent advantage. The reality is that when you and I are using our phone, we care about data, we care about performance, we care about latency. And so model efficiency, a design concept that around power efficiency at the edge is fundamentally important. And so we're seeing use cases already running efficiently at the edge, from mobile phones to home appliances, even the car, are great examples of power efficiencies. But again, the idea is not just a single architecture. You need a CPU, you need a GPU, you need an accelerator. And for us, we're using this notion of a compute subsystem as a way to bring performance, power efficiency to the edge with the right size model to make it a viable solution.
With your permission, I want to summarize what Dylan Patel say about edge computing. There are very few narrow use cases that latency really matter for word completion, and most of the user wants to do a big job. Here is a deep research task. Here is something that you need to thought of with reasoning that take huge amount of compute, and they want the frontier model, the biggest one, that's on the cloud. And the latency of sending small amount of data, like image, video, compared to the amount of execution need to generate, and like GPUs getting hit, crunching all this data is huge. So I don't think that the future is around edge, but on cloud, data center, deployment. Now, I do want to go back to the original question, which was how bleeding edge frontier models are going to look like, and the answer is no one knows. No one knows what the models of the future are going to be at. I mean, right now, transformers and LLM is the future. Just a reminder, a few years ago, it was convolutional neural network, and company literally designed a chip tailor-made for a specific function of the CNN, and when attention came, it's all about attention, this hardware, became a brick. Designing a hardware chip costs $150 million, around 3 years until you get into a point that you are production ready. That's the amount of investment you need to do. So designing now a chip that etch llama weights inside the hardware, that's stupid, because 4 years from now, it's going to be a new architecture, a new model. No one here knows what it's going to be. And obviously not me. I'm like a software engineer at heart designing 3-nanometer chip. But what I do know is that your hardware that you're going to design must be a future-proof. We at NextSilicon, we decided to go and accelerate science in high-performance computing, the most complex code on planet Earth. We run them out of the box on our hardware. That means that for NextSilicon acceleration in the future, whatever math that is going to be invented, we will be the one that will be future-proof and can accelerate the future.
In addition to the 150 million that designing a CPU costs, you have to put the hundreds of millions or even billions of dollars of ecosystem software enabling so that the legacy codes run on it, so that there's interoperability. So it's really, you have to think twice before designing a chip because it will be outdated when it comes out.
And I think on this topic, actually, it's something that through the venture lens we've been seeing quite a bit, is that in order to kickstart those ecosystems, there's of course the technical breakthroughs that are needed in order to make it happen, but then you need that adoption from the developer community and have companies understand, when they're making a decision to go ahead with you from a hardware standpoint, it's a strong commitment, and they need to know that they'll be able to have the support and the channels to enable their development. We've seen a lot of different entrepreneurs go after the opportunity of trying to solve hardware challenges with a software layer. And it's been interesting over the past, I'd say, 3-4 years to witness how it's not been that trivial. And I think, you talked, Elad, about future-proofing, and that's something that of course, we try to reason as well from the venture lens when we make investments into the transformer architecture or others, is what will that mean tomorrow? And there's a big question around I think, if people are here today at the conference, it's the belief that there's a lot of value that's being created, but for the model providers, there's a question of the value capture. If we think about, we play that out into the future, and maybe more towards the quantum side of things, how do you feel about the heterogeneity of the different approaches that exist in compute, and how maybe quantum can provide interesting solutions to that?
Yeah, I mean, I think like some of the discussion that we've just had around edge and some of the things that you just mentioned, like it's nice to think about these things, but let me put it this way: like, I'm just not worried that edge computing, for instance, will happen. Like, it's going to happen. What I'm worried about is big fabs, AI supercomputers, nuclear power stations, and building a useful quantum computer, which has been my life's journey. And very like accurately made point, this huge investment to build these things, and that is a uncomfortable reality of the world that we live in, which is that value is forged on the frontier. Value is forged by organizations that work for decades and spend billions of dollars to realize these capabilities that we're now, basking in the riches that are being created by that. And so, yeah, our company, we tend to take that fairly abrupt and maybe aggressive position that, for instance, with quantum computing, I could go and raise money and tell a nice story that it's going to sit on a benchtop and that it's going to be hybrid and it's going to be nice and low power and so on. The reality is you have to build a giant million-qubit error-corrected quantum computer if you want to realize the dream applications that we are talking to customers about. And that has been the DNA of our company from the beginning, is to recognize that uncomfortable reality and get on with doing it. And Intel did amazing things in establishing the fabs and 18A and so on and so on. OpenAI, of course, worked away for a decade without anybody knowing about them. That wasn't a breakthrough, right? Like, that was a deliberate decade of work that got them to that point. And so, yeah, that is my perspective on a lot of this discussion, is that there's quite a lot of tendency to wishful thinking and to free lunches, but really the value is forged in some of these grander and more uncomfortable realities.
And so maybe if we're talking about that value creation at the frontier, could you walk the audience through a bit what those sequential steps, where are you at in terms of those dominoes that are falling into place to help you unlock that value? Because I think that a lot of booths today are talking about the imminent value capture of AI. If we play it out on a longer term horizon and talk about quantum, where would you locate yourself? Where would you situate yourself in terms of timelines?
We're building a machine, and again, it's easy to forget that AI was also like a failed field, right? It would, like, some of the reputation that quantum computing has as a never-ending research project, a bunch of academics with some nice ideas in a lab, they're messing around, it's not for real. The same things were said about AI for a long time, defunded by DARPA, defunded by UK government, viewed as an academic curiosity for a long time. And I started out in a research lab doing science experiments on a benchtop. I think in the last few years with quantum computing, we've seen a few things. We've seen major milestones hit that skeptics said would not happen in my lifetime.
Could you articulate what some of those milestones have been?
Yes, so error correction. So actually being able to actively control errors in real quantum processors. Various people told me I would not see that as long as I live, that it's just too complicated, it's fantasy, it's whatever. And that's now being done by many different teams all around the world, really successfully, exactly the way it was supposed to happen. And again, that's described in the press as a breakthrough. It's not a breakthrough. It's something that people said they were going to do 10 years ago, and they worked like hell, and they delivered it, and it works exactly the way it's supposed to. We've also seen quantum processors now where a single chip can win a race with $1 billion leadership class supercomputer. That is not for a useful application, but it is a glimmer of the kind of exponential computational power that has put me on this journey. And then, yeah, I think people who understandably, very understandably, see quantum computing as a science experiment that's never going to come real, might be surprised to see the maturity of where we're at. So we are now making thousands of wafers of quantum chips in the production line of a tier 1 semiconductor foundry. We've been doing that for many years. We've spent north of $100 million, put 10 new mainframes into the fab. We're building these chips shoulder to shoulder with chips that go into laptops and cell phones. We've gotten rid of the chandelier that is so famous. We're building nice big 3-ton cryostats with a contract manufacturer who normally does food and beverage and pharmaceutical industry contract manufacturing. And we are breaking ground this year on 2 roughly 200,000 square foot, roughly 100 megawatt sites in Australia and Chicago. In each case, we have about $500 million of non-dilutive government support for us to build those systems. And we're not going to build it in 112 days like XAI famously did with that Colossus system. We're going to go a little slower than 112 days. But I do think we can build this much faster than is conventionally anticipated, leveraging the same contract manufacturers, OSATs, fabs, etc., that we use to, as is so wonderfully illustrated at this conference, build giant systems in a matter of years. We're trying to do exactly the same thing.
So I agree with you, and I would like to say, if people believe that quantum will not happen during their lifetime, they are absolutely wrong. Intel Labs has been doing a lot of quantum computing. I don't want to talk about it. But what I know now is that quantum will happen at some point in time. We will need millions of physical qubits to be able to work on hundreds of thousands or millions of logical qubits to run some software. And if I want to take an example, which is decryption or breaking codes, people say, oh yeah, we already have the technology or the algorithm for post-quantum computing. And they say it will come later. Wrong. They have to implement today in their applications the post-quantum algorithms, because when these applications run in 10 years and there's a quantum computer that will be breaking their code, they will not be post-quantum ready and they will break. So people have to co-design their software with not only what exists, like NPUs or GPUs, but also with what is coming next, like quantum computing, QPUs.
And that makes for a perfect transition on the architecture side.
And that was not scripted.
No, that was not scripted. On the that's one of the topics. You talk about the importance of post-quantum work and being ready for that time horizon. I think a lot of entrepreneurs have a hard time quantifying and assessing that time horizon. And so then, in terms of the stack rank of priorities, it's not always easy to prioritize in the roadmap how to think about this. Broadening it out beyond QPUs. We've talked about GPUs. There's talks about CPUs, TPUs, FPGAs. What are your thoughts from a perspective of architecture? Do you think that there's going to be this government of slew of specialists? Is there going to be an emerging architecture that manages and orchestrates those different architectures as well? Maybe Elad, to kick you off here. You talked about some of your software approach. Maybe you have some thoughts on that.
Yeah. So the big question: software versus hardware foundation. Companies are saying, "Behold, that's the best chip out there. We have 1 nanometer fabrication and lots of chiplets, lot of HBM, but dear developer, just rewrite the entire software of the world into that chip." That's not going to fly. I mean, NVIDIA is an amazing company and the only one that was able to integrate a domain-specific language, the CUDA, into the ecosystem and environment, and CUDA is a fact of life. There is just trying to do a marketing tomorrow 9:20 with Dr. Ian Curtis in Ada Lovelace. We have a session, hardware versus software, super interesting fireside chat. Essentially, my perspective, it's all about software. It's all about software feasibility. People used to write in general purpose languages, C, C++, Fortran for supercomputing, Python code. Move to CUDA. CUDA is a fact of life. next generation compute in order to ease the transition, not to invest trillions of dollars in software ecosystem, is the one that be a drop-in replacement, meaning taking existing software and run it on the architecture. We worked so hard for 7 years on a chip that can reconfigure itself, that understand the different computational kernel, reconfigure the chip so we can have a drop-in replacement, a chip that can run CUDA. That's what we invested so hard and so long for. So the future is not going after domain-specific chip. Here is an FPGA. Here it's going to be classical computer. Obviously, CPUs are mandatory, best-in-class for serial execution. RISC-V is the future. ARM is the future. x86. Who knows what the future is going to be, but you need the acceleration portion that will be a general-purpose one. And obviously, quantum, which is above my pay grade. Don't understand anything about that, but that is going to accelerate few problems that no one else can solve ever in our lifetime.
But that's what some people have said about those specialist architectures as well, is that it will help solve some what people would qualify as niche use cases, but that are very deep applications. Maybe here for Pete or for Will, how do you feel about those types of challenges that people are posing, saying, CPUs are good for X or QPUs are good for Y?
I have a sort of extremist view on this.
Go for it.
Which this is said with self-awareness, right? There are people who fundamentally disagree, and I respect them tremendously. But my novice's assessment of history is that the generalized architectures tend to win out in the end. And this idea of application-specific hardware is very sticky. It's very attractive, and it makes things sound easy and cheap, and it's a fun idea to think about. We've just seen this happen in quantum computing, where for the last decade, there's been a lot of wishful thinking that we could build small application-specific processors, avoid all of the error correction, maybe do some special encoding that's good for chemistry or good for something else. That's basically dying, and everyone is rapidly reverting to universal, error-corrected, textbook, normal quantum computer. And that, to me, looks like what happened with three-state logic. People used to try and do three-state logic for conventional transistors, for conventional computing. Turns out zeros and ones just kick ass all day long. Same with CPU, same with some of this matrix multiplication. I mean, that's a pretty general thing to be able to do. And so I'm pretty pessimistic. I think it's unfortunately an endlessly attractive idea that just doesn't actually survive scrutiny.
Well, look, I mean, custom silicon is real. So when you think about NVIDIA's Grace Blackwell architecture, it's a combination of the ARM Neoverse CPU and an accelerator. When you look at what AWS is doing, that is a custom silicon. So Graviton is a custom silicon. Microsoft, custom silicon, again, still based on ARM. Google, custom silicon, still based on ARM. And so the idea that there is a place for general purpose compute, but there's also a place for custom silicon, which means application specific. When you know the workloads that you're trying to accelerate, when you know the data that you're trying to compute, custom silicon makes sense, especially in a world where power is not free. You can't constantly keep just drawing power from the power grid. You have to think intelligently about the workload. You have to think intelligently about what you're trying to execute. And so, the same way that if I'm building a tunnel from here to England, I can use either a shovel, I can use a jackhammer, or I can use a tunnel boring machine. And so you have to think deeply around what it is that you're trying to compute, and then choose the right tool, choose the right architecture to enable you to do that. I also agree that software is critical, right? Not just in terms of the software stack. We're making sure that you've got a developer community that really understands backward compatibility as well as forward thinking. And so it's all of those things. It's not one versus the other. You've got to think about all of the parameters and design with the end in mind.
But just on this, I think what's tough is that the developer mindshare of those different architectures and software layers is unfortunately not as forward-looking. And so you've got those kind of bunny hopping exercises of people moving from one environment to another because they realize that the wind is moving and that they need to adjust to a new reality. And so that's maybe also why on the quantum side, from a developer ecosystem standpoint and the post-quantum readiness, people will shift all of a sudden, and some will be ready and others won't because they just won't have prioritized it at that point in time.
So I totally agree with you, Will, that both CPUs, GPUs, accelerators, custom solutions are needed. We need CPUs, and they run the world at the moment. But there are a lot of tasks that can be accelerated or that can be done in a much less power envelope. And that's very important. That's why at Intel, in all of our CPUs, we have some cores that do the work that we need. And then we have plenty of accelerators, like some AI accelerators. But we also know that there will be a need for some bigger, discrete accelerators. And they are needed for some very specific tasks. And we also are sure that everyone needs to have access to all of these. That's why we have created the Intel Foundry, where we, of course, manufacture our own CPUs, but we also offer them for those who want to do their custom solutions. So we have some experience, proven experience on designing CPUs, manufacturing them, packaging them, and we are offering that to the world. And I think that it's something that will help facilitate access to all of those accelerators that we will be seeing, NPUs, GPUs, QPUs, etc.
Great. Well, look, I think now is the time for us to wrap up. So I'd like to thank all the speakers for their contributions, and thanks to the audience.